Oh.
Yeah. Yes. Okay. Can you hear me? Yes? Okay. So, you've heard now Feliciano explaining a bit why Wannier functions may be useful for calculation of properties. What I want to tell you in this hour, and then also later, next hour and the first part of the afternoon, is what Wannier functions are and how you can compute them using the Wannier 90 code. So I'm Giovanni, and also later Antimo and Valerio will show you something about the code and will be helping you during the exercises. One thing that I put here, you have the slides on the internet, are some references. There are some reviews and some original papers which explain the method. And then I will mention later after the coffee break a bit about the code. There is this website. So let me start, and I want to start with the theory to explain you how you compute these things, what Wannier functions are. So I want to start from the very beginning. So you know we have crystals, and we describe crystals with periodic boundary conditions. So this is a unit cell. Since you use periodic boundary conditions, you can represent bands in the reciprocal space over the Brillouin zone. So in the one-dimensional case, if the lattice constant is A, you go from minus pi over A to pi over A. And the key ingredient you will see we use a lot is the Bloch theorem, which tells you how you can write a wave function in periodic boundary conditions. And I also try to use a bit the blackboard. So in case you don't see, let me know, so I'll write a bit bigger. So that's really important, we'll use a lot, which is the wave function. I just repeat it because it's going to be used a lot. It's a function of space, okay, and has two indices, band index and a k-point index. Can be written as the product of a periodic part, okay, times a phase. And where u is really periodic, which means that if you have u of nk at a point r plus capital R, where capital R is a lattice vector, a periodicity vector, this is the same as unk of R. Okay. So for the next slide, I will just start with a simple assumption that is this plot, if you want, that you only have one band. So I just drop the index n, and then we see how to introduce it back later. And so I just have this simple expression. So if you have a simple band, it's relatively easy to define what the Wannier function of the system are. And I define them like this. So this R is the index which defines the Wannier functions. And what you have is basically, if you want, it's a Fourier interpolation of the wave function on each of these k points over the Brillouin zone, okay? And this R is an index, and it's an index which represents the different lattice vectors in real space. Now, a few properties of this. As I said, there is one per lattice vector R. And if you imagine to have a big crystal, so in one dimension it would be, you know, n unit cells, 1, 2, etc. You can imagine that in reciprocal space you have n k points you want to consider, okay? And so what Feliciano was also saying before, this is just a Fourier transform. It's just representing the same Hilbert space. It's just a change of basis set, but you don't lose information, okay? If you think in the usual way as wave functions, you have capital N objects, because you have capital N k points you can consider. When you do a Fourier interpolation, you will have capital N Wannier function. So you have one Wannier function somewhere here, let's say something, let's say, with a p orbital-like shape. And you have n copies of them. And then what I want to show you is that indeed, this index, if you change the index, you choose a different lattice vector, you just get a copy of the same Wannier function shifted in a different unit cell. So let me try to write this down. So I use this definition. So my Wannier function, if I use the index r, it's what I write there. I can say this is kind of a function in the end. It's an index and depends on where it's defined. And this is just, this formula there, is the integral on the Brillouin zone of psi k of r times a phase. Okay. And now I want to see what happens if I take another lattice vector. Okay, so imagine this is some r. Let's say maybe it could be, if that's the origin, it's r equal to 0. And then I want to consider another index r prime. Okay. So let's see what I get. I consider the function, for instance, in W r plus r prime of r. So it's another lattice vector. What I get is just, I use the same definition. It's uk of r e minus ak times, and here I just replace, okay? And I get r minus r prime. Okay, and just here so let me just first write this. Maybe the easiest way to see it is to replace psi with its formula here. So you have bz u and k of r a I k r minus r. Okay, here I just replaced psi with this formula, and so I get an ikr here minus r. That's the definition for r. If I choose a different index, r plus r prime, I just replace here the index, okay? Now, what I can use is the fact that u is periodic. Okay, so I put here, instead of r, I put r minus r prime, and I split this. So what I get in the end is just bz r minus r prime, and here I just collect the terms. And if you see, so here I just replace this with this, which are the same because of periodicity, and here I just collected a term. Nothing fancy. And if you see, this is nothing else but this function, okay, where I just call, instead of r, I define r minus r prime. So this is just the function with index r defined at point r minus r prime. Okay, so this is just saying that if you take when you change this index, you're getting the same function just shifted. And so you can interpret again that if you have n unit cells in just one band, you have one function will be localized, let's say, in this home cell. And when you change the index, you have another one here, another one here, another one here, shifted. So that's what I shown on the blackboard. Now, the question comes now if I have more than one band. So if one band, it was easy. If I have more than one band, what I can intuitively do is just do the same. I now have an index n, and what I want to do is to just do a Fourier interpolation for each band, and I define n Wannier functions. This, you can do it, but you will see that very often doesn't give you a very good answer, in the sense that typically you get a function which is not localized, which is not what you want, because as we said, we saw before, the aim is really to have something localized so you can use it for efficiency and to say where things are far away, the interaction is 0. And so the first thing you notice is that actually here we made a choice. The code gives you back the wave functions, psi, with a random phase. At every k point, you have a phase which can be different from the next point. So the first thing you can realize is you can do the same thing using a different phase in front of each wave function. Okay, this is something that, as I said, this is something the code decides for you randomly, and you can change it and you just get a different basis set, but the physical properties are the same. However, if you think about it, here you're doing a Fourier interpolation. Okay, you're integrating over the Brillouin zone, but if at each point I change my phase, also the Wannier functions will change. And we'll see what happens if the localization change. So by changing this phase, the shape of these real space Wannier functions will change. And what we will want to do is to choose the best phase, in a sense, that minimizes, just localizes the Wannier functions. But this is not the most general thing you can do. So that's one thing you can do. More generally, what you can do is to apply a unitary transformation to the psi. And this, therefore, is the most general transformation you can do by keeping a basis set, by modifying it, by basically rotating the basis set, and then you do the Fourier interpolation. So any unitary that you choose will give you a different shape. And the problem we see in a few slides is really to minimize some kind of localization of these orbitals, these Wannier functions, by changing this U matrix. So how can you understand this U matrix? So I said the simplest thing you can imagine is just a phase. So for real value function, we'll just be changing the sign. It's still the same valid basis set. You can imagine really as a rotation. So imagine you have two states now, two bands. At each k point, I want to mix these two states, but not randomly, but I want to basically do the unitary transformation you can imagine as a rotation, and just changing basis set by rotating my vectors, and so preserving the length and the angles between them. You think it's a typical way you change basis set when you have an orthonormal basis set and you want to change it. And so that's just the interpretation of this U matrix. Okay, so this, very generally, what we're going to do, to change basis set k point by k point in order to obtain, at the end, after Fourier interpolation, something which is localized. Here I just summarize some important facts I just mentioned, which are these Wannier functions span the same space as the psi. Okay, so it's really just a change of basis set. You go from something which is very delocalized, like the psi, to something localized, but it's really a different basis set, nothing else. And we saw in the blackboard that the different R are just translational images at fixed n. Okay, so if you have n bands, you will have n different Wannier functions, different shape, but then you have a lot of copies of them. And one thing I didn't mention, but it's a property that you can easily show, and it's very important, is that even the Wannier functions are orthonormal. Okay, you start from orthonormal psi, and also the Wannier functions you get are orthonormal. And so you can apply, for instance, to an isolated group of bands. Okay, so in the case, for instance, of an insulator or a semiconductor, you forget for a moment about the conduction bands. And for these 4 bands, for instance, in the case of silicon, you mix for every k point in the 4 states here. You do this calculation. Sorry. And the question is, how do we choose this best one? So we need to first choose what is the measure of localization. We have to define a measure of localization. And the measure of localization, which is used in what are called the maximally-localized Wannier functions, which are the one computed by, for instance, the Wannier 90 code, which we'll see later, is what is called the Foster-Boyce localization function, which is this one. Okay? And you can understand it. It's very easy. It's just telling you basically the spread of your Wannier functions. So if you imagine, for instance, in one dimension, that you have a Wannier function which is a Gaussian shape, for instance. So imagine that it's your real space, and you discover your Wannier function as this shape. So this is, for instance, the square of the Wannier function. Okay, and this is a center R0 and some spread sigma. If you compute this quantity is nothing else than just integrating R minus R0 square times the square modulus of the Wannier function. And you see that if this is normalized, this is nothing else than sigma. And the second term, if you want, so that's the whole part, okay? This one, you can easily see that's basically the sigma, okay? And the term which is squared inside is nothing else than R this R0, that's what we can say it's the center of the Wannier function. So you have this very simple, you integrate the Wannier function times R, the value R, and you get the center of the Wannier function. If you do R minus R0 squared, just R subtracting the center and multiply by R squared, you get how spread it is. Then you do this sum over n, you sum over all Wannier functions, and you get omega. So omega, if you want, tells you the sum of the spatial extension of all Wannier functions. And the aim will really be to minimize this quantity, so to find something which is very localized, okay? And how we change it, it's really a minimization problem where we change u, and we compute every time this Rn. We see, but technically it will be done a bit differently, but the idea is you change u. For every u, you do this calculation, you compute the Wannier functions. For these Wannier functions, you compute this quantity, and then you, in an iterative way, you minimize this, what is called the spread, okay? Now, an interesting thing is that you can decompose this function, this spread, in two components, which are called omega I and omega tilde. And this is quite important because we'll see later, we can perform the minimization on each of these two parts independently. And the idea is that you can write, so omega as a sum of omega I plus omega tilde, okay? These are the expressions. You can show it if, maybe since I don't know if I have enough time, I will go ahead. I won't show you mathematically on the blackboard that it's really positive definite, and just give you some ideas. If maybe we finish early, I will come back and show you this on the blackboard. But the idea is really that you can prove that in this part is easy. This part is clearly positive definite because it's sum of square modulus. So this number is clearly positive. It can be shown that this part as well, it's not difficult to show, this part as well is positive definite, okay? It's always positive. And moreover, one can show that this part, omega I, is gauge invariant. So gauge invariant, just because maybe I didn't explain it before, means that when you change this U matrix, you change what is called the gauge, you do these rotations of the basis set, this quantity will not change, okay? So if you do the minimization and change U, only omega tilde will change, and these two quantities are positive. So when you want to calculate the minimum of omega over all possible matrices U and K, you have calculated the minimum of a sum of two positive numbers, and this doesn't change. So in the end, we will see that we can do only the minimum of U and K of omega tilde plus omega I, which doesn't change. That's the same, okay? So this simplifies a bit our work, because what we can do is just compute this and minimize this part. Okay, as I told, I don't know if I have enough time, so I will skip this mathematical proof, and if I have time, I will do it at the end. Okay, so now numerically, we have to compute this spread, and our ingredients will be the solutions computed with Quantum-Espresso or another DFT code. So how can I compute, for instance, a matrix element like this, where I have Wannier functions and R in between, or Wannier functions and R squared in between? Well, if I take the definition of Wannier functions, okay, that's just by definition, that's a Wannier function, it's just a different notation, and that's my psi. And here I apply my block theorem. Okay, if now I multiply by R, you see that I can get R by just calculating the gradient of EIK times R. And this will, if you do a gradient, this brings me down IK. So if I multiply also by minus I to remove the I get that if I multiply minus I gradient of K of EIKR, I get just an R in front. Is it clear? So just the gradient of this is just IK times EIKR. Now, I do an integration by parts. So you have an integral of a gradient times a function. I do integration by part. I change the sign. I bring I outside. And so I remain with EIKR times the gradient of UK, okay? I just did an integration by parts. And so you see that now if I do the sandwich on this side, when a function is just nothing else that this integral of this ingredient, where you have a gradient in between UK. Okay? So that's for R. If I want to do R square or in general higher powers, it's very easy to do the trick more times, and then we get powers of this gradient and of I. So that's the general formula, which is true for many functions. If you do, these are called Blount identities. If you want to compute the L moment of R, you just have to, you can do it if you have the functions obtained from the periodic part of the wave function obtained from DFT, for instance, by just computing gradients over K space. Okay, this is a gradient, so a derivative when you compute a U in a given K point and then a U in the next K point. And indeed, this helps us understand how we can numerically compute these quantities. So in the code, what you have is this U and K over a grid, typically. And you have to numerically compute these derivatives, and the way you do, you use finite differences. So what you will do, you will ask your Quantum-Espresso or VAST or whatever code you use to compute your U and K on a grid. Okay? Let's say this is, for instance, 4 by 4. In each of these, you get U and K. Okay, it's K 0, 0, 0, 1, etc. And then in order to compute these derivatives, you actually compute by finite differences by taking, for instance, if I'm here, I will compute also the U here and use this 4 to obtain the derivative at this point. Okay, so the derivative at this point will be typically, for instance, this minus this over this distance. And you see that when you do then the sandwich, you have to do, in the end, U and K, the gradient U and K. This gradient can be expressed as, if you want, something of the form U and K plus B minus U and K with some factor to divide by the length. And so you see that the main ingredient, this is, so it's orthogonal, so you get either 1 or 0. But the ingredient you get in the end, so this, if you want, this is this. The ingredients you get is something of the form U and K, U and K plus B. So this is integrals, overlaps of periodic parts of the wave function over neighboring points in the Boolean zone. So you will have to ask the code, and we see there is an interface for that computed for you, to compute the U in this grid and then take neighboring points and compute the overlaps of the functions you computed in the neighboring points. Okay? This matrix is called MMN and depends on 2 band indices and a K point and B, which is where you move a small shift in K. Okay? And this we'll see later in the code is one of the most important ingredients you have to compute, you have to ask your code to compute. And the interesting thing, that's really maybe one of the few, if you have to remember a few things, if this I think is important to remember, you can, not these formulas, but the fact that you can express the center of the Wannier function and the spread of the Wannier function just in terms of some mathematical expressions which depend only on this MMN. So you can compute the localization, omega. You don't need to know the explicit expression of U on this grid, but you just need to know the overlaps MMN. And so this is important because it means that once you have these matrices, we can compute already, we can perform a minimization and find the Wannier functions without having to know anymore the U. So you have to imagine from a cost point of view, knowing the U is expensive because you have to take, for every K point you have already n bands. And then for every n and k, you have to take a big grid, the one using DFT, I don't know, 60 by 60 by 60 points in the unit cell, depending on the grid on the G vectors you use. And so you have a lot of big files. If you just want to minimize the spread, you don't need this. You just need to have, I don't know, imagine you have 4 by 4, so 4 Wannier functions. In the case of silicon, you have a 4 by 4 set of matrices, 1 per K point, times a few neighbors of the order of 6 to 12. So in the end, you have something of the order of 100 4 by 4 matrices. So just with these few numbers, you can compute omega, and so you can minimize omega. That's very important. You will need to have the explicit form of U only if you want to show the Wannier functions in real time. We'll see later in the code how these files are managed. Okay, so you do this, you compute this MMN, and if you minimize the spread, you get something which is as a shape of a localized function. Here I show just some few examples. That you have benzene here, you have silicon amorphous, and then silicon and gallium arsenide in crystalline phase. Later in the exercises, you will see silicon, for instance. What you get, these Wannier functions are really, so these are, oh, sorry. These Wannier functions are really, you see, localized. This is just two atoms. So these are really functions which are localized basically inside a unit cell and go quickly to 0 out of the unit cell. And kind of resemble the chemical bonds you expect. For instance, in a benzene ring, you get orbitals which are close to the bonds, okay? Now there is an important thing to remember though, which is so both a mathematical feature, but also is important from a numerical point of view. So first, mathematically, you can prove with some assumptions, especially if you have an insulator, that these Wannier functions exponentially decay far from the center. So we chose the correct U to minimize the spread, to keep them local, but still you don't know, the minimum could be for a function which is still very, very wide, okay? Or maybe just that, it's localized, but has a tail which is very, very big. Instead, you can show it for Wannier function coming from the valence bands. You have something which far away goes down exponentially. So you can really say that, for instance, if this is your unit cell, typically you have something which is 0 far away and not 0 just close to some atoms or some bonds. The other thing which is important to know, there are some mathematical proofs for this under some assumptions. In other cases, it's just heuristics. We know it always is like this. So Wannier functions are just Fourier interpolations of complex wave functions. So nothing in principle tells you that the Wannier functions you get are real. What happens is that in practice, at the real minimum, if you minimize omega, the Wannier functions you get are real functions, okay? And that's actually one of the ways you will have later to check if your Wannierization is correct. So in the code you will see you put some inputs, you get an output, and you want to know if what you get is correct or not. Sometimes it doesn't, because you might go in a local minimum. So you have your functional and you have a local minimum, but it's not the real place you want to go. And so one way to check is to see if the Wannier functions you get are real, and the code at the end of the Wannierization, if you also ask to plot the Wannier functions in real time, will print the maximum value of imaginary over real, actually the absolute value of this, over the whole grid. So you compute the Wannier functions, check the imaginary value and the real value, and tell you the maximum. If this maximum is basically 0, 10 to the minus 6, it means it's a good indication that your Wannier functions that you computed are correct. If this number is of the order of 10 to the minus 2, 1, or larger, then probably your Wannier functions are wrong, and you will see also a little later in the band interpolation. That's the other way you have to check. But that's an important way to check if your Wannier functions are correct. But it's important to tell, this is a minimization algorithm, and it's implemented in the code as an iterative algorithm. So you start it from an initial guess, and you go down with minimizing this U. Actually, you can define a gradient, so you can really do a gradient optimization until your algorithm converges. But unfortunately, this doesn't guarantee that you go to the global minimum. And so it's important to provide an initial starting point. So you say, I expect my Wannier functions to be roughly this. And if you choose a good one, the algorithm will bring you down to the correct Wannier functions. If you choose a bad one, typically you get the wrong Wannier functions. You get stuck in a local minimum. And the way you can give initial guesses is by telling to the software, look, I expect that I have, I don't know, a Wannier function more or less here, which is a shape which is more or less like an s orbital. Or maybe I have three Wannier functions there on this atom or in this specific place in space, which are maybe p-like orbitals. That's something, that is the critical and difficult part, if you want, of computing Wannier functions. You will see later Actually, in the exercises, we tell you already what the Wannier functions look like. We tell you already these initial projections. When you will have your own problem, your own system, not always it's obvious to understand. You need a bit of exercise and physical intuition and chemical intuition of where this could be. But this is really important because we see if you don't have the right A, typically it's hard to get the right Wannier functions. And the way you do it is you decide these orbitals. Okay. Typically in the code we see, we say, okay, I have silicon, so I have 2 silicon atoms. Okay, please put me, s orbitals and maybe, or sp3 orbitals on each silicon. Or maybe you say, put in this position s orbitals. You pass this to the interface code with your Quantum-Espresso or VAST code. And the code we compute these A matrices here, which are nothing else than the projection of your s or p orbitals or whatever you chose onto your wave functions. And this is another ingredient which we give to the code. Before we saw the M matrix. So that's the first ingredient. Let me write it down. So the first ingredient you need is this M, N matrices. These are the overlaps. So these are really essential to know to do minimization. One ingredient is mainly a numerical ingredient. Mathematically wouldn't be necessarily needed. Are these AMN matrices, which are nothing else than projections of your guesses onto the wave functions. Then there is a trick to make these matrices unitary. I don't want to bother about this. The code at the beginning makes them unitary. But the message I want to give you is really that you have to give these initial projections. So one important reason why we compute Wannier functions is that because it allows you to do an efficient band interpolation. Okay, and that's very similar to what Feliciano said before and what we saw yesterday for phonons. If you compute in the end your MMN, your overlaps on a coarse grid with DFT, let's say for instance 4x4x4, 6x6x6, this is a typical order of magnitude for a small unit cell, then of course you don't have a band structure. You just have the energies at these 64 points. But instead, often you want to do a band structure interpolation, or even more, density of states, for instance, and you need to do a very dense sampling of your Brillouin zone in order to get an accurate result. The advantage of Wannier functions is that they allow you to do a very efficient and accurate interpolation of the bands. So the idea is that this, again, is just the formula you already saw before. That's your Wannier functions. Your U that you optimize. So at the end of optimization, you have one specific U. You can write it down. For each k points, you have n by n matrices, and you have written on disk. You apply them, you apply on psi, you do the Fourier transformation, and you get this. And typically, these k points are, say, the one in which you actually do the integral are small grid. Now, the idea is that you can Fourier interpolate back, okay, these results, and obtain the Hamiltonian matrix at any k point just by doing a Fourier interpolation. So what you have to do is basically actually take your Hamiltonian at the k points on which you did your DFT, apply U on the right and on the left, is basically a change of basis set, do the Fourier interpolation on this. This already is very interesting. This gives you the matrix element of the Hamiltonian between two Wannier functions of different type, NMN, maybe one is S, one is P on a different atom, and centered in two different unit cells. That's already a very important ingredient, and then the idea is that if you use this and do a back Fourier interpolation, so you do a forward and then a back Fourier interpolation, you can do this in any k point, and you get an interpolated matrix, Hamiltonian matrix at a different k point. You can diagonalize it and get the bands. Now, this is very important also to understand a bit the meaning of the interpolation. So you can really imagine that if you take, as what Feliciano said before, so if you take you're going in reciprocal space. So this would be my Brillouin zone, and I take, let's say, I do in 2 dimensions to draw it. I do a 4x4 sampling, okay? So I have 16 k points. This corresponds in real space to consider, so if I go in real space, to consider a 4x4 supercell. Okay? So if I have, say, my atoms, I consider a 4x4 supercell. And when I do my interpolation, I only basically consider, I will have matrix elements only between Wannier functions within this big supercell. So I will have matrix elements with R equal to 0, so in the same unit cell. Let's say this, for instance, if you have two bands, one S and one P. So I have this hopping. I can have, if R is this one, I have other hopping and so on, up to this distance. And what I'm assuming is that by choosing, so that's the meaning of, you have to do convergence on these sides of the grid you choose. What you're doing, if I say 4x4, you're saying I expect that my functions are so localized that Hamiltonian matrix elements far away are basically 0. So that's a real important ingredient, if you want. What you're saying is that my functions are more or less localized here and here. If I know that, I know if they're exponentially localized. If I know that my matrix elements here and here are basically 0, I can stop there. And basically, when I fully interpolate back, I put to exactly 0 anything which is far away. That's the idea of the Fourier interpolation, and the idea why this works very well, because you get very localized Wannier functions. We'll see later, after the coffee break, an example of silicon, which is an example we'll do in the afternoon. And Antimo and Valerio will show you that actually, for instance, in silicon, if you do just 4x4x4, you get an interpolation which is already reasonably good, but not perfect. Already, if you go to 6x6x6, the things improve a lot. Because in that case, it means that still there is some overlap between things which are at distance 4 unit cells, okay? One thing I want to mention here, so that's just another take-home message which I just mentioned, okay? One thing just is a numerical thing which is still important, is that when you do, actually I did this but I needed it, so I can just do it again. When you do a 4x4 grid and you do your Wannier functions, so in a case of an infinite sampling, your Wannier functions are really localized in a given place, and then go to 0, and they're 0 up to infinity. In the code, we don't do infinite sampling, we do finite sampling, we do 4x4, for instance. This means that if this is my real space, okay, and these are my Wannier functions, the code will not return you something which goes to 0 and 0 at the infinity, but if this is my unit cell, actually it gives you one Wannier function going exponentially to 0, and then its periodic replicas, okay, let's say in this case, 4, 8, 12 cells apart. That's important because if you try to plot it, you will see this. And this also is important when you try to approximate the fact that these matrix elements are close to 0. So you're actually not computing, so in 1D, imagine just doing 1D. Okay, if I do my Wannier functions here, number 1, let's say, and Wannier functions here, number 2, actually I'm not computing the integral between 1 and 2 and then 0 elsewhere, but I'm actually computing the integral of this times this one. Okay? Which, if you normalize, if they are far away and you normalize by the unit cell, it's typically very close. So the idea is that if you, another way to see the importance of this grid, if you take a very dense grid, this goes far away, and the function has really a time to go to 0 before finding its periodic replicas. If you take your grid to small, at 2 by 2, for instance, what you have is that imagine your function, that's your unit cell. Imagine your function goes to 0 exponentially, but not very fast. Okay, it would be like this. If you take a 2 by 2 sampling, you're actually summing another one here. So here you get some error. This doesn't have the time to go to 0. So the idea is that you want to have a sampling which is dense enough so your functions have the time, in a sense, of the space actually, to go to 0 very well, and then you have another copy. And when you do the matrix elements, these are exactly the same as doing the matrix elements of a function which really goes to 0 at the infinity. So in the last 15 minutes, I want to speak about an extension of this, which is very important for what we'll have to do, which is the case of entangled bands. So up to now, what I've been discussing was just the valence bands, or anyway, a case in which there were a set of bands which are mixed between them, like the valence bands of a semiconductor, but they were separated by an energy gap from all other bands, okay? Because I didn't say it explicitly, but that was what I needed to do, because I started with, if you remember at the beginning, with the case of one band, and then I extended this to the case of n bands. But still, I assumed that, for instance, if this is silicon, okay, that you have some valence bands, and then you have some conduction bands, and I only want to focus on some bands which are disconnected from the rest. Now, this is possible for insulator or semiconductors if I just want to look at the valence bands, but either in this case, if I want to look also at the conduction bands, or in the case of metals, here I have the case of copper, this is not even possible. I have a set of bands which are entangled, and I never have a place where I can say, okay, I cut here, those are my valence bands, and those are my conduction bands. And what I want to do is still to get some kind of Wannier functions which are still good to either tell me the nature of the orbitals or to do a good interpolation for at least the bands I'm interested into. For instance, if here I have a Fermi energy, I just want to have good interpolation for bands below a certain energy. And if you look at the bands of copper, copper is another of the examples you will see later. Either if you have a bit of experience with band structures or a bit of chemistry, and say you will understand. You see here that these are basically in the anti-crossing of 5D bands with an S band here. So typically S bands are very dispersed and do something like this, while D bands are very narrow and do something like this. When you put them together, okay, you have D orbitals and S orbitals. They anti-cross. There is some hopping between them. And so you don't get, of course, just this, but actually you have some mixing, okay? Something like this. And that's what you see here. But you see it far away from the anti-crossing, you have something which is almost parabolic. It would be the band which comes from S orbitals. And these bands here come from the orbitals. Here, close to the crossing, you have some mixing, of course. So what we want to do here, for instance, in this example, I would like to get some good approximation only using the orbitals of what the bands would be if I didn't have any S orbital. That's one of the possible applications. And you see the Wannier function in this case really come out to be very D-like shaped, okay? And how can we do it? That's 2 slides to tell you how you do it. I don't want to go into details, but I want to at least explain you and make you understand why it works. Before we remember, we wrote that our function, our spread omega could be written in 2 parts. So it was omega equal to a gauge invariant part, which we forgot about because it wasn't changing with the gauge for the U matrices, and a gauge-dependent part, which was the part we were minimizing. And so we kind of forgot about this, and we were minimizing and writing down only this part. Actually, now we see that this part instead is what we want to minimize in order to get a good, what is called disentanglement. So disentangle other bands from the one you really care about. So I tell you also how it works in the algorithm and the idea. So you take, typically, at least in the code, a given energy window, okay? And you say, okay, I'm interested only in things in this energy range, okay? As you take a fixed energy, for each k point, the number of bands you have will depend. So for instance, here I have 6 bands, here I have 1 more, 7, and so on. So at every k point I have a different number of bands. But then I'm interested not in all bands, but just in a subset of them. For instance, here I know there is a D manifold, a set of D bands inside, which have degeneracy 5. So I say, I would like to find the 5 bands which don't change too much when I move over the Brillouin space, okay? So I have to fix n, I have to know what this n will be. N has to be smaller than nk at each point. So of course, if I want to find 5 bands at the one point I have 4, I cannot do it. But if I have more, I want just to find a projection, if you want, a matrix which takes my 6 bands and brings me down in a space of dimension 5. And to do this, we see that what you have to do is to minimize this omega I part. once you go from a 6, 7-dimensional space down to a 5-dimensional space everywhere, with the condition which is, this also is a smooth over the Boolean zone, then you get something which is very similar to what you had before. So something where at each point you have the same number of bands, and then you can use the same algorithm as before to minimize omega tilde. So the idea is really what has been shown by Ivo Sousa, David Madabet, and Nicola Marzari, is that you can split the problem into parts. A first part where you take all your bands and you go down to a space of lower dimensionality. And once you get there, the algorithm is exactly the same as before, the one we saw before for Wannier functions. And also in the code you will see when you ask to do this entanglement, there will be a first additional part which prints some numbers, which is the minimization of omega I. And then the algorithm is exactly the same as the one you will have used before. So what does it mean to minimize omega I? So that's the expression omega I. You can show that omega I measure the change of character of your Wannier function, so the change of shape, if you want, of symmetry, over the Boolean zone. So if you want, if you take, so the simplest way I think to explain it is if you take two states of different nature. I'm zooming on a band structure, okay, so this is my K-space. That's my energy. And they have a state that we call 1 and a state that we call 2. So that's 1 and that's 2. If you have some interaction between these two states, that's not what you get an anti-crossing. So the actual band structure will be something more like this, where here it's 1, very far away, and 1 here. Here is 2. But close to this area, you have some combination of 1 and 2. Okay? So while you move across the K-space, okay, this point changes state from 1 to 2 in a continuous way. Okay, this state changes from 2 to 1 in a continuous way. And so if you compute the overlap of u, or the wave function, the periodic part of the wave function at a given point, and then the neighboring point, so here and here, if the function has the same character, this will be basically 1. It's orthogonal. If this function, let's say these two are orthogonal, if I go from here to here, these two u's will be orthogonal. So will be the overlap will be 0 because 1 and 2 are orthogonal by two different states. So you can prove that the larger the overlap is for close K points, the smaller omega I. And since you want to minimize omega I, if you apply a numerical minimization algorithm, what you get is that you're choosing bands where the character doesn't change too much. Now, for two bands, maybe it's not very clear, but when you start imagining again the case of copper, we know that here, if you take a state here, it's very S-like. If you take a state here, it's very D-like. And here in between will be a mixture, okay? So if I ask the code, please take only states in this window. And here I'm showing an example with a different window. Here I'm choosing this window, and here I'm choosing this window. And find me only 5 states in a way that the character of the state doesn't change too much across the Boolean zone, okay? I want to minimize this change. Here, for instance, I only have 5 states, so here I know exactly what the state has to be. In fact, you see here the bands are very well reproduced. When I will have to go out of my space, because of the minimization, the algorithm will try to follow and keep the D-like state and discard everything which is S-like, okay? If I increase the window, here I'm including also other states. I'm only telling the algorithm, please find me the best 5-dimensional space, but I'm not putting any specific constraints if you want. So in fact, you see here the bands are a bit different because it will pick up also some S character up here. So we still find, if you want the spread here, the omega I will be smaller because there's more possibility to choose. But in a way, it's not perfectly D-like orbitals because you will use a bit of S to minimize the spread. But that's not a very important, I mean, now like the specific example. What I really want to pass the message is the meaning of omega I. Is really make sure that when you move across the Boolean zone, the character of the state doesn't change too much, or change the smallest possible. And the reason, by the way, why do you want this? Because in the end, you have to start from the U and K and do a Fourier interpolation to go in real space. And you know there's a general property of Fourier interpolation. The smoother you are in one space, the more localized you are in the reciprocal space, okay? So you want something which, the smoother your properties are in the Boolean zone, the more localized the finite functions are. That's why, if you want, that's why this is true intuitively. So you want something which is very smooth. Yes? No. So this would be the real bands of a material. You take a real material, okay, you have some band structure, and you look at the bands and you discover that there is an anti-crossing. You know, you see it very often. I mean, here, if you want, this is an anti-crossing with these bands. Here is a bit more complex. So maybe I show it here because otherwise you don't see. So here it's a bit more complex. We have 5 bands anti-crossing with 1, in a sense, well, 6 anti-crossing together. But if you want, the fact here, this is doing this, and these bands are staying here in between, it's an anti-crossing. It's a physical property. It's the fact, if you want, that these 2 orbitals have a non-zero hopping, okay? The anti-crossing side is given by the hopping energy between these 2 orbitals. And so physically, if you do, you know, if you take Quantum-Espresso, you take 2 bands which cross like this, and you take the U and K here and here, and then you take the U and K here and here far away, you see that basically this and these are very similar, this and these are very similar, and these 2 are orthogonal by construction because the code gives you always orthogonal orbitals. Just because the bands would be this, but if you go across the center, they are mixed. If you do a simple model with 2 bands, you see exactly this. You just make a tight binding model with 2 bands, 2 energies, maybe depending on K, and then you put a hopping, a non-zero hopping out of so basically you get a matrix which, as a function of K, has two energies, a 1 and a 2, and then you have some hopping, non-zero hopping here, okay? This non-zero hopping will split your gap. Sorry? Yeah, it's this number in the end, apart from some numerical factors. And this number is just, you know, the overlap between localized. If in a tight binding model, would be the overlap between orbitals. So what maybe I didn't say before, maybe I'll tell it now. Let me just go back maybe to the slide where. No, they are still orthogonal because it just typically one is 1 plus 2 and the other is 1 minus 2, but they are orthogonal. Okay, but the code, the code always gives you orthogonal states for the given K point. It's just that they cross in a way to be orthogonal. The idea is that really, you see here you have localized orbitals. Okay, maybe I show it also on this side. Here you have localized orbitals, and these are the matrix elements between these localized orbitals. So if you know tight binding, it is nothing else than a tight binding model. You're saying I have this would be the hoppings, okay? The diagonal elements are when you're looking 0n, 0n, and the other are the hopping between different orbitals in different places with different shapes. And actually, Wannier functions, if you want, is an efficient and accurate way to get a plane wave basis set and obtain a tight binding model with few neighbors, because that's the idea. You have few neighbors, and the other one you can cut to 0. So just to mention a couple of words, sometimes you hear speaking about spillage. That's basically this, so how much state of the wave function you lose while moving between K points. And as I said, in the case of copper, the drawing I was showing before, I choose a 5-dimensional subspace. For instance, if I were looking at these states. And of course, the code does, if I just tell the code, please find me a 5-dimensional space, it doesn't know it has to choose D orbitals. It will choose the best 5-dimensional space, as it happens here. But if I choose, for instance, in this case, a window which is only of size 5, it knows here has to be D, so we'll try to preserve it. Just to make a different example, if you want to look at a S orbital, you just have 1. And as I was telling you before, intuitively, here you have the proof in a way. That's your S band. And the code finds something which is a much bigger spread. You see here was 1.7. It's a very localized D orbital. Here, here it's a much larger S-like orbital. And that's your orbital. And if you do something, which is actually what you actually do in basically always, you don't care about, here you have some bands which are similar but have not much to do with the original ones. The same here, okay? They have S-like here are in between. Very often, actually, if this is your, let's say, Fermi energy, you want to have a good, ideally perfect interpolation of your valence bands. And then on the conduction bands anyway, maybe your system is not occupied and you don't care. Or maybe you still need some conduction bands to be well interpolated. And then above a certain energy, you don't need anything. So the idea is that what we will do in the code, we'll define two windows. One, which is called the outer window, is the one I've been speaking up to now. So it's basically the big space from which you want to mix the states and find a lower dimensional space. And this drawing will be this one. And then there is a smaller window, which is called the inner window or frozen window, or different names, which is a window where you enforce, you ask the code, please make sure that the energy of these bands is exactly reproduced. So the algorithm will try to make sure that the interpolation goes through the same ab initio energies at the points where you calculated it. And you see that if you use this, here the bands interpolate very well the energy. Before, you see, it was okay, but it was already starting to depart a bit. So it was not a perfect interpolation. Here, up to here, it's perfect. And then above, it does something to minimize the spreads again. So it's not a, you see, the difference from here and here. But in the end, very often, maybe you need only to know about valence bands or up to here, and you don't care about what happens up there. And you see, in order to do this, you go from something which is really S-like, in a sense, apart from some bumps. To do this, you have to take a bit of the character. And in fact, if you look at the Wannier functions, you have a kind of big S-like blob, kind of almost a sphere, plus some D-like contributions near the other atoms. But in the end, as I said, you often care about this case, and you will see in the exercises that you have to specify a frozen window, not only for metals, but also for insulators. I still have 2 more slides, and then we go for the coffee break. So this is the case of silicon. It's your first 2 examples. You can do 2 things. You can interpolate only the valence band first. I get these 4 bands, and I get, in the end, what is called bonding orbitals. I get orbitals which are S-like, let's say, and are centered at the bond center. Okay? And then I can do, just consider these bands with some disentanglement. And what I get other 4 bands. I ask for other 4 bands, the best 4 bands which are defined in this manifold. And I get the anti-bonding states, okay, which look like this. And the spreads are these. Now, the other thing I can do, and what you typically do, instead you take this as a window. You do just 1 vanillization. Here you do 1 and 1, 4 and 4. Here you do just 1 vanillization with 8 states. And what I get instead is something where the total spread is smaller. It's 10 instead of being 24 plus 7. And you get sp3-like orbitals. Okay, you get 4 of them around each atom. These are atom-centered, and they have 4 of them. So what are the messages here? So 1, since you do 1 minimization in a larger space, you give more freedom, and so you can minimize more the spread. And this actually gives you, so in both cases, you have a different physical intuition of the problem. They're both correct. But typically, for instance, if you want to have a very localized state, this is better because the spread is smaller. The other message is that disentanglement is important not only in metals, but also in insulators, if you care about the conduction states. And the other message I want to give you, because it's practically important when you do interpolation, is that that's the outer window in this case, and that's the frozen window, for instance. So the frozen window here, I'm saying, I want to reproduce very well the valence bands and do the best you can in the conduction bands. But the important thing I want to focus here is now the outer window. So here I chose this, and you see my interpolation gets these bands. This is a message is important not to choose a too small outer window, because the states you want to get will be only taken from within this window. If you chose this window here, at this point, you didn't have enough states to interpolate and to keep a smooth variation of a WN zone. So you have to be careful, because sometimes you will see in the simulations you get very bad results. Sometimes it's just because maybe you chose a window which is not high enough. You're cutting away in some k points some states, and the algorithm has to do something to keep things smooth, but has to choose other states. This is a simple case, because here you have nothing else, but it's more complex when you have a lot of bands coming in between. And just to show you, this is the last slide before the coffee break. That's the case of a carbon nanotube where you have S bonding states between bonds plus PZ orbitals orthogonal to the tube. And you see here, it's a clear example. We have a lot of states which mix together. But the interpolation, the red and blue ones, that's the Wannier interpolation of the DFT bands which are in black, works very well. Okay, it's basically identical. But here, one has to be very careful because there is a lot of crossing. And here you see the window that were chosen were this for the inner window and this for the outer window. If here you choose an outer window which is below, like here, okay, at each k point maybe you have enough states to get, I don't know, 12, I don't know how many there are here. But this entanglement will not be able to do something smooth. And you get something which is either not real or the band interpolation will get very wiggly. And you discover that your band interpolation is wrong. So that's an important take-home message. When you have, you want to do this, to choose a window, give a look to the bands, try to understand their nature, maybe do some projected density of states if you don't know, because you want to get all the bands which have a given character, okay? So I think I'll stop here. We can go for the coffee break. I don't know how much we have.